Come to the survivors. There's a steep fall off on Friday, but hopefully this will not be too elementary to the people in the room. Ask me questions though, as much as possible, so that it's not just one way. So I wanted to talk about hidden zeros and splitting in the Associahedron. Most of this talk will be based on recent work by Arkani-Hamed, Jin Dong, Songhe, and Carolina Figueredo. This is 2024 and 2023. And then towards the end, I will try and incorporate things that I've been thinking about related to such topics. Okay, so broadly, the kinds of theories that they were looking at in these papers were color-ordered theories. And they were the usual suspects. They were NLSM, trace phi cubed, and Yang-Mills, and this other theory called Yang-Mills scalar that we'll talk about in a second. Yeah, but because these were color-ordered, you can divide the kinematic space into planar variables, which we saw in Alok's lecture as well. And then, yeah, non-planar variables. And if you have a spinning theory, you also have some polarization information, which will come in terms of these Lorentz invariants. Okay, good. And so clearly, when you have a color-ordered theory, the only poles that you have in your amplitude are going to occur when xij's are 0, and not when cij is 0. Now, clearly, there's some exceptions, so I should say cij when I minus j is greater than 1. Okay. Yeah, so there are no poles, and in addition, this forms a basis. And the crucial thing when we are constructing the Associahedron will be to swap out some of these basis elements for these. And this will allow us to treat some of them as constants and some of them as variables. But okay, that's going a bit further. Let's first just look at how these variables show up. So if you look at n equals 5 trace phi cubed, yeah, then you have graphs of this type. These are the only type of graph. And then you decorate it with your labels, and you're allowed to sum over cyclic permutations of these labels. So in terms of the x's, this is just x13, x41. Yeah, 1, 4. Same thing. Plus cyclic. Okay. Now, if I were to sum over all of the cyclic permutations, then you get something which is f, some function of the variables, which are x13, x14, x24, 25, 35. Divided by, again, all the locations of the poles. I've just put them under a common denominator. And because each of these has to, basically this needs to be cubic. Okay. So as you can see, it's non-trivial from looking at this pole structure to figure out what are the properties of this function f. This is also something that Song brought up in his lecture about when you're multiplying BCFW terms together, you know where all the poles are, but it's non-trivial to actually write down the individual terms that come out of that square when the sum over, when the BCFW expansion itself is large, right? So this is similar. I mean, this is it's much more trivial looking 5-point case, but you can see that this polynomial is going to increase in degree and it becomes harder and harder to say things about the polynomial. Okay. And the main thing that we will want to say about the polynomial is where does it vanish? Okay. Now, this is a kind of dumb question because I could always say f of 3 vanishes when this happens. This is a condition on the x variable, right? So really what I mean, and this is a cubic condition. So what I want over here is a linear condition. Okay. Okay, good. And before I talk about how to figure out where this happens, I just want to introduce you to one kind of bookkeeping, which is called the kinematic mesh. Okay, so I mean, there are maybe ways of giving this more structure, the kinematic mesh, but for us, it's enough to just think about it as some way of bookkeeping all of your variables. So you start with a mesh, so you give these points on a line labels in this way. Let's do 6. Okay, and then you draw these 45-degree lines. Okay, and then you say 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Yeah, okay, and then you join the lines in this way. Okay, yeah. So then each of the vertices is an Xij. Each of the Cij's is a plaquette or diamond, whatever. It's one of the small regions over here. Okay, so then you basically give each of these. So this is x13, x14, x15. x16 is 0, x12 is 0, so I'm not going to write them. x24, 25, 26, x35, 36, and x46. Okay, and then each of the diamonds above an x, I call C of that. So C13, C14, C15, etc., etc. And each of them obey the following equation. Cij equals xij plus xi plus 1 j plus 1 minus xij plus 1 minus xi plus 1 j. Okay, which is just the x's which are on the bottom and top and left and right of the diamond that the C lives in. Okay, so as I said, this is just a nice way to bookkeep and to see what the kinematic space looks like. For example, this triangular region over here gives you all of the variables you need to describe a 6-point amplitude. And the smaller kinematic region over here, this triangle, gives you all of the information you need to describe a 5-point amplitude. So actually, when I go on to x15 equals 0, then the mesh just splits into this part and this part, which is precisely the 3-point amplitude, which has no kinematic invariance, and the 5-point amplitude that has these exact kinematic variants. So x1, 3, 1, 4, 2, 4, 2, 5, and 3, 5. 5 of them. Okay, good. So some of you might remember these exact equations from Alok's lecture, because these are exactly the equations that will carve out the associahedron for us. Okay, so how does that work? So I should say in particular, when I say associahedron over here, I mean the ABHY associahedron. So this was used by ABHY. Don't have the year, so I actually don't remember the year. But yeah, but when I say this, it's a way of giving geometric meaning to some combinatorial object. The combinatorial object is an associahedron. And this equation is what is giving it some geometry. It's telling you what lengths mean in that space. And those lengths will be C. We'll just plot it in a second and you'll see that those lengths are C. So let's continue with our n equals 5 example. Yeah, I do the 6-point mesh. We'll come back to the 6-point mesh, but let's do n equals 5 ABH1. Okay, so the first thing you have to do when you're plotting an ABHY associahedron is you divide your basis elements into variables and parameters. So your variables are going to be, so you ultimately you want your amplitude, which looks like this, to be a canonical form on some space. So the number of poles is the number of boundaries, it's the number of dimensions. So you want to choose two of your x's. So let's choose x13 and x14. Okay. And because this is not a basis, you have to additionally add 3 parameters, which are your c's. Okay. So for us, that's going to be c13, c14, c24. Okay. Now, using these equations, I can write down what x24 is, which let me do quickly. 13, 14. I can write down what x25 is. 4. And finally, the last of my x's, which is this. Now, why it's important to write down what the x's are is that you know that this is exactly where you want your boundaries to lie. When this equals 0, you want there to be a boundary of the space. So now I can just plot. I can say that, all right, one of my boundaries is x13 equals 0 and x14 equals 0. This being 0 is basically saying that, or rather this being greater than 0 is just saying x14 has to be less than this value. So I can say x14 has to be less than this point, and this point is just c14 plus c24. Okay. This line again is similar, but for x13. Maybe let me draw it further out. Yeah. So this is x25 equals 0. This point is c13 plus c14. Then finally, there's a third line, which is this, which is x24 equals 0. I think this is c13, and this is c14. Yeah. Okay. So this is the ABHY associahedron, often called A2, which is a bit confusing because it's the 5-point amplitude, right? But it is just this, n minus 3. So it's called A2 because it's 2-dimensional. It has these appropriate boundaries at the correct locations, and each of the vertices are now compatible boundaries, meaning that if I write down the boundaries correctly, so like this is x13 equals 0 and x35 equals 0. So I just say 1 over x13, x35 plus x35, x25 25, 24, 24, 14. And this is literally the trace phi cubed amplitude for the ordering 1, 2, 3, 4, 5. Okay, so nothing mysterious here. You can literally use your kinematic mesh to choose variables, to write down equations that will carve out your associahedron. Canonical form on the associahedron gives you gives you the amplitude for trace phi cubed. Okay, good. But there's something you should notice about this, which is, basically there are limits of my parameters where this space is going to shrink to 1 or 0 dimensions, right? So if you look at, so if I take C14 to 0, then this line is going to flatten down like this, right? In addition, this line is going to move downwards until it hits C24. So if I take C24 as well to 0, I have not only flattened this, I've also pushed this down. And that leaves me with exactly this just one-dimensional space when I do that. When I say C14 equals C24 equals 0. Yeah, and the canonical form on this is 0 in these variables because it's one-dimensional. So now I can do it instead of squishing it downwards, I can squish it to the side. And so I can take C13 to 0. So now I get this like triangular region. I don't know if you can see it. Like that. And then I take C14 to 0, pushing this line in. So that is again another limit, but that is a limit that looks like this. And to understand why these limits exist or what they give you, we have to understand something called a Minkowski sum, which Nima briefly mentioned in his lecture yesterday. Okay, so the Minkowski sum of two sets, A plus B, are elements of the type x plus y, such that x belongs to A and y belongs to B. Okay, very innocuous looking definition, but there are nice things you can do with it. So for example, a point Minkowski summed with a point is a different point translated by the other point. Yeah. A point Minkowski sum with a line is another line, again translated by a point. Okay. Now let's do something more interesting. So a line like this with a line like this gives you the parallelogram, right? Let's do right, where this length A, B is A and B, right? So in this way, you can come up with figures. And you can see that the dimensionality of what you get out is it's not that clear what you're going to get out, right? So I mean, in this case, I summed two lines, I got something two-dimensional. I summed a triangle and a line, and I still got something two-dimensional. So this is something unlike the combinatorial pictures we saw where you put the tubings on different edges that are like, you put different graphs on different edges. This is sensitive to angles, lengths, things like this, right? So this is a geometric thing. And it turns out, so maybe, yeah. So we want to get to the pentagon, right? So you might have thought that the way to do that is two triangles, right? Two triangles, though, two triangles will give you a hexagon. Yeah. Where I'm not going to specify, but you can play with this and see that this actually works and that various side lengths here go into side lengths here. Okay. So what does give you the pentagon, which is what we would need in order to write the n equals 5 associahedron as a Minkowski sum. So the pentagon is given by a triangle plus a vertical line plus a horizontal line. Yeah. Where this is the triangle, this is the vertical line, and this is the horizontal line. And just to match with what you have over there, the horizontal line is C13, this is C14 in length, and this is C24, and both these sides are C14. And then this will become exactly the n equals 5 associahedron. Okay, good. And now that you have this Minkowski sum representation of your associahedron, you can say the following, that when C13 equals C24 equals 0, then all I'm left with is this triangle component. Okay? And the triangle component is two-dimensional, so I don't get a 0. On the other hand, if I do C13 equals C14 equals 0, we saw that this is one-dimensional, and so it results in a 0. Similarly, C14 equals C24. Okay. Are there any questions about this logic? Okay, good. So both of these have something in common, which is that if you go back to the mesh picture over here, they are both closed rectangular regions in my mesh. This is C13, C14, which is this small rectangle, and C14, C24, which is this small rectangle. And apologies, I should have drawn the 5-point mesh, but picture there is a line here, right? And so this is a closed rectangular region, and this is a closed rectangular region. And so it turns out actually for trace phi cubed that at any endpoint, any rectangular region gives you a 0. Okay, so what is the statement? That for trace phi cubed, color ordered 1 through n, this equals 0 when all the s's in some rectangular region of my kinematic mesh vanishes. So these are what I'm going to call 0 of m type. So this is Sm1 plus S1 n minus 1 S n minus 1. Yeah. So for the 5D case, this would be Z2. Okay, plus cyclic meaning this is Zm, but there's also cyclic permutations of Zm. Okay. Okay, good. So I just want to point out that for n equals 6, there are 2 types, which is this type and this type, right? So this would be something like S13, S14, S15 equals 0, whereas this is S14, S15 equals 0, S24, S25 equals 0. But they're just rectangular regions in the mesh. Okay. Okay, good. Now, by themselves, you might think that this is very, very singular and so gives us basically nothing. But it turns out these zeros are enough to fix a lot of theories at leading order. So it's actually quite a constraining principle. And if you look at this 0 in particular, right, this one over here, it's one step away from Adler. So it's one step away from a soft limit. So if I had also add C12 equals 0, right, then by momentum conservation, this would mean C15 is 0, which would mean that P1 has gone to 0. So this is a soft limit. So this is actually more constraining than a soft limit. To say that your amplitude vanishes in this limit is more constraining than saying that it vanishes in the soft limit. I will say that in the case of trace phi cubed, you also know that the amplitude doesn't vanish in the soft limit. It's singular in the soft limit. So the fact that it's 0 on this is kind of surprising. Okay. Good. I will say though, if this was the end of the story, I think it would not be as interesting. But the amplitude itself, so A trace phi cubed, splits on the support of, or near the 0. So if I go on to Zm, and I choose one of these S's to be non-zero, so Sij star doesn't equal to 0, where Sij lives in one of these. Then the amplitude looks like A4, some fixed A4. We'll come to what exactly the arguments of all of these are. A bottom and A top. So what do I mean by A bottom and A top? I mean in the kinematic mesh, if you look at a 0 region, maybe I should have just printed out a kinematic mesh in this talk, but like, so this is the region for the 0. So it'll split it into something which is at the bottom and something that's at the top, right? So this is what I'm calling A bottom and A top. And near the 0, once I've chosen one of the S's to be non-zero, my amplitude splits. Now, when I say this arrow symbol over here, it's not a limit. This is an exact equality. So I'm saying literally, if I take all of these S's except 1 to 0, this amplitude equals kinematically this. Maybe I should just say equals. Okay, so it's not a Taylor expansion, it's not a perturbative statement, this equals this. The amplitude genuinely splits. Okay, good. Yeah, so let's put some, let's give one example. So example, A6 on Z3 S25 not equal 0. Again, this is not an arrow, it's equality. So the first A4 only depends on what type of 0 you are. So it's always going to be 1, 4, 3, 6. And then in this case, A bottom and A top are both 4-point amplitudes. So you get 1, 3, 2, 6. And A top is 3, 5, 4, 6. And all of these are trace phi cubed amplitudes. Okay. So here, if I wanted to generalize this, this would be all x's in the bottom triangle. This would be all x's in the top triangle. And this would remain a 4-point amplitude, no matter what, which is where these two border the 0. Okay? It's not important what the rule is. The point is there is a rule that allows you to predict what happens in such a kinematic corner of your space. Okay, so what was the statement of Arkani-Hamed, Cao, Dong, He, and Figueredo, 2023? It was that these Zm is a 0 and splitting for the following theories: for NLSM, for trace phi cubed, for Yang-Mills, and Yang-Mills scalar. Okay. Now, I only showed you the associahedron for trace phi cubed. I'm not going to go into it, but you can look at their paper. In their paper, they show you exactly how to do a deformation from trace phi cubed and reach these other theories. Okay. So, yeah. So because of that deformation, you can show that the properties that trace phi cubed has, in short, these zeros and splitting, is inherited by these deformed versions of trace phi cubed. Okay. There is, of course, a difference between all of the scalar theories and Yang-Mills. So I've not told you anything about spin or polarization or anything like this. So to do that, we have to understand how to scaffold gluons. This is related to what is this theory of Yang-Mills scalar. Okay, because I think the nonlinear sigma model we still saw in Alok's lectures how to get to, but we've not talked about Yang-Mills scalar yet. But it's basically Yang-Mills, meaning some gluons, coupled to an adjoint scalar. So this is the interaction. And what this allows you to do is, so if you write down the actual amplitude, it's very easy to write down. This is literally the only thing you're allowed to write down. Yeah, and now in this case, so when P1 plus P2 square equals 0, any amplitude of this type is going to split into phi, phi, gluon, and gluon with the rest of the amplitude, an minus 1. Okay. What this does for you is it allows you to now, on the factorization channel of these fully scalar amplitudes, get a gluon. So I can talk about scalar amplitudes, but then secretly I know that I'm talking about gluon amplitudes, right? So the momentum of this gluon is P1 plus P2. And because of this amplitude, so basically what am I doing here with my Feynman rule? I'm stripping off epsilon 3, and I'm putting a mu here, a nu here, and I'm sandwiching an eta mu nu here. right? So effectively what I've done is I'm saying that polarization of the gluon is P1 minus P2. So if I talk about scalar amplitudes in this theory, so a scalar in Yang-Mills scalar, all I need to do is go on to the following locus. I have to say that S12 is 0, so let me put all the S's, S12, S34, S56, dot, dot, dot equals 0. And then what I get out is a fully gluonic amplitude. So this is A Yang-Mills. Okay. So you should have questions about gauge invariance, but if you don't, then I don't have to talk about it. So yeah, gauge invariance works out. It's a bit, I mean, you have to just be a bit careful about what you mean by all of these things. Yeah. So you can always, so basically you've managed to, in D dimensions, I should emphasize, replace all my gluonic amplitudes by scalar amplitudes, but 2n scalar amplitudes. Okay. Okay, great. So now if I tell you that Yang-Mills scalar amplitudes have this property of having zeros and splitting, we can now just say, all right, I write down my zero conditions over there, except I use this translation, right? And I now want to rewrite the zero conditions in terms of q mu, which is the momentum of the gluon, and epsilon mu, which is the polarization of the gluon. And I can just do this trivial rewriting. Okay. And so Zm spin, so these are d-dimensional Yang-Mills zeros, are just when you say pi epsilon j, epsilon I pj, epsilon I dot epsilon j equals to 0 for all ij and Zm with no spin. Okay. So if C13 or S13 equals 0 is the correct 0, for example, at 4 point, example, n equals 4, m equals 2, then it's S13 equals 0 for Yang-Mills scalar. But for Yang-Mills, it's saying that epsilon 1 P3 equals epsilon 3 P1 equals epsilon 1 dot epsilon 3 equals 0. So these are d-dimensional gluon zeros that just come from the scaffolding. In addition, you can also see that the amplitude has to split. So 6-point Yang-Mills will then again go to A4 chase phi cubed, because that's just some prefactor. And then A5 5 phi G G G times A3 G G G 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, okay. Okay. Good. Yeah, okay. So I think this is all I wanted to say as an introduction to what I mean by zeros and splitting. So are there any questions what I mean by this class of zeros, what are hidden zeros, what does splitting mean near these zeros? Okay. Are all the linear zeros? It's a good question. I mean, I'm tempted to say yes, just because they come from this Minkowski sum representation. But I suppose there's some question about like how invariant this representation is, which I'm not sure what the answer to that question is. But I'm tempted to say yes, these are the only linear zeros for trace phi cubed. For NLSM and for Yang-Mills, I think the answer is no. Yeah. And that's kind of because they don't actually come from the Associahedron. There's no like geometric description for them. And so you just have the like stringified U variable construction of the surfacehedron or surfaceology construction, right? So if it comes from that, it doesn't come from this, and so there's no Minkowski sum in that case. But for trace phi cubed, I'm tempted to say yes. Okay. Okay, so now I wanted to connect to something that JJ introduced us to over the last few days. So these theories, you might notice, are color kinematic dual. Okay, so what this means is that they satisfy the BCJ relations, which was one of the last things maybe that JJ introduced us to yesterday before going to loops. Okay, so let's just look at n equals 4. It's a very simple relation. It's 1, 2, 3, 4, S1, 3, S1, 2, 1, 3, 2, 4. Okay, so this looks very simple, but there's a lot of physics you can pull out of this. So let's first look at NLSM. So the nonlinear sigma model of pions only has 4-point interactions. There are no 3-point interactions, which means both of these are local functions of the Mandelstam. If they're local functions, then I know there's no pole in S1, there's no pole in S13. So when S13 goes to 0, that means A1, 2, 3, 4 has to be 0 because it satisfies the BCJ relation. Okay. Bijoint scalar. Okay. Now trace phi cubed has only one color. Biadjoint has 2 adjoints. But trace phi cubed amplitudes can be written as the diagonal elements of biadjoint scalar, which is color kinematic dual. So you can do the following, where I've just chosen my second ordering on both sides to be 1, 2, 3, 4. Now here, initially, there would have been a pole in S13, but because it's not compatible with the second ordering, there's no pole in S13. And once again, I can say that when S13 is 0, because of the BCJ relations, this has to vanish. Okay, good. Let's now look at Yang-Mills. Now, Yang-Mills, you know there is a pole at S13 equals 0. There are 3-point interactions, and those 3-point interactions we saw in fact, in my previous lecture that they're very important. They give you on-shell diagrams, etc., etc. So there's definitely a pole, but you know exactly what happens in the pole. On the pole, so let me just say that okay, let's just look at this side. So limit S13 goes to 0 of just 1, 3, 2, 4. Okay, so you know what happens on the pole. It needs to look like A3, 1, 3P, A3, P2, 4, right? Yeah, divided by S13. But you know exactly what these 3-point amplitudes are. So let me just write this 3-point amplitude. Epsilon 1 dot epsilon 3, epsilon P dot P1 plus epsilon 3 dot epsilon P, epsilon 1 dot P3, epsilon P dot epsilon 1, P. Okay, so these you'll see are exactly the spinning 0 conditions we wrote down over there, right? So this is 0, this is 0, epsilon 3 dot P is epsilon 3 dot P1, which is also 0. So this 0 condition carefully makes sure that on the pole, one of my 3-point amplitudes vanish. And because one of the 3-point amplitudes vanishes, there is no pole at S13. And once again, I can then say that because there's no pole at S13, 1, 2, 3, 4, when on the Z2, whatever spinning, I forget what I called it, spin, 0. This happens for Yang-Mills. So basically what you've shown at 4 point is that having color kinematics duality guarantees you the presence of these zeros. Okay, good. But as we saw from our understanding of the double copy over the last few days, is that it's not just color order theories that participate, right? So it's the BCJ relations that tells you something about gauge theory, but you double copy it into gravity, right? So the hope would be that you take this and you double copy it, and then in your uncolored theories, with no color ordering, no partial ordering, you still have zeros that look like this. And so you still have zeros that look like they have some artificial ordering, right? Okay, so let me just quickly say that this argument, color kinematics duality, you can show at n point, which is what we did in this paper, Brown, Barch, Kampf, Octum, Paranjape, Trnka, 2024. That CK duality actually implies hidden zeros. Okay. But doing this allows you to actually include more theories. So now df square also is there. All higher derivatives, all higher derivative corrections are now included, etc. So basically, anything that is color kinematic dual has to have these zeros. It's got nothing to do with the Minkowski sums, etc., which is where they began. Okay, so now let's do the double copy. Okay, so let's do the same thing as before. Let's look at what happens at 4 point, and then I'm going to say this generalizes to n point. So M1234 equals S13 A1324 times A1342. Okay, good. Yeah. Okay. So let's first look at NLSM times NLSM, which gives you the special Galilean theory. Now, clearly, again, no two particle poles, no S13 equals 0, and so this works, right? Because S13 vanishes on the right, so it has to vanish. So this thing over here has to vanish. Everything is local. Okay, good. NLSM times Yang-Mills equals Born-Infeld. And once again, because of the argument over there, this also has to vanish on ZM spin. Right? So this includes some polarization conditions for Born-Infeld. And then finally, we saw that Yang-Mills times Yang-Mills equals gravity plus antisymmetric B field plus a dilaton in d dimensions. Actually, I'm not. Did JJ talk about this? I think he did. Okay, well, I mean, you have a polarization here, you have a polarization here. And so when you double copy them together, you get something which is symmetric, which is the graviton, something that is antisymmetric, or maybe I should call it B, which is the antisymmetric 2 form, and then the trace, traceless symmetric, and the trace then gives you the dilaton. Yeah. So when you double copy Yang-Mills, you do get, you get pollution from these two fields as well, and you have to take them out if you actually want to get gravity. Yeah, okay. So in this case, it's true that you can go through the same argument and prove that Yang-Mills has no poles, but then there's a question of what is happening to your polarizations. Okay, so very often what people talk about when they're doing the double copy is what is called the fat graviton, which is actually the graviton field that comes directly from, most naturally from the double copy, which is just this. So this field contains all of these fields. And unless you subtract out some trace and you symmetrize, you're not going to get the right answer. So just to say that this KLT argument shows that the fat graviton vanishes on ZM spin. But you have to be more careful. You have to project out the states that you actually want to show that it vanishes for the polarizations that you're interested in, right? Yeah. In other words, both these have to satisfy the zero conditions. And so like once both of these satisfy it, then this satisfies the zero conditions, but you still only get the fat graviton. So you have to do the correct projection. I will say one thing, which is that we are in D dimensions. So in 4 dimensions, something nice happens where you have only 2 states of the graviton, and this is exactly plus times plus and minus times minus. So in that case, you don't have, unless you really try, you're not going to get the dilaton, which is this, in 4 dimensions, or the antisymmetric B field. And you get it, but it won't get polluted from here. All right. Let's see. What else did I want to say about this? Okay, yeah, my last comment. So this was an LSM, Born-Infeld, gravity. And then finally, I wanted to talk about closed string amplitudes. Okay, so the original way of writing this KLT relation was to write closed string amplitudes as open times open. In that case, M1234 is sine pi alpha prime S13. This actually continues beyond this 4-point example. So like at any endpoint, you're replacing S by sine of S. But what that means is that now my 0 locations have just moved from Sij equals 0. Now I get Sij equals n over alpha prime, where n is an integer. So you can show that closed string amplitudes to n point now have to have zeros at these locations. And they don't even have to be for ij, it doesn't even have to be the same integer. So this gives you an infinite number. Okay, there was already an infinite number of points where you knew that the closed string amplitude vanishes. This gives you another infinite, n times infinity number of points where the closed string amplitude vanishes. Okay. Simply from looking at what are the consequences of the KLT relation. Okay. Okay, good. Any questions about this? Okay. So I'll just end this double copy part by saying that just like in the same paper, just like we showed CK duality implies hidden zeros, you can also show that KLT implies hidden zeros. And yeah, again, this will now include F cubed, R cubed, other higher derivative things, conformal gravity. DBI. So if any of these theories are of interest to you, you can possibly, you know that they will have hidden zeros, and you can use that now in your methods of bootstrapping if you want amplitudes in this theory, in these theories. Okay, good. Okay. So I had some extended remarks that I wanted to make about this entire thing about studying the Associahedron and its consequences. So the first was about recursion and factorization. So notice that I have not said anything about splitting, or maybe I should say splitting. I'm not saying anything about splitting near these zeros coming or that its relationship to the double copy. So I'll say a few words about that. Then I want to talk about G vector shifts. And then I just want to advertise some upcoming work on cosmological correlators, or as I have been taught to say, wave function coefficients in DS. Good. Okay. So yeah, and Nima's set of lectures should have told you why what we talked about today is very related to wave function coefficients in DS. Okay, good. Right. So as promised, we will now look at factorization, and we'll look at it in terms of a recursion relation. So in the beginning of my last lecture, we talked about how you do splits, you do residue theorems, and those give you some recursion relations, right? So in this case, you would want your recursion relation to look something like AN on this special kinematics, evaluated on this special kinematics, let's say A6, evaluated on special kinematics Z3 with S2 5 star not equal 0. You would like that to be some shifted amplitude, but evaluated at 0, right? So that you can write this as a contour integral like this, right? I've not told you what Z is, but the point is you want to design a shift Z so that this is true, right? And then eventually you would like then this to be a sum over residues. And that sum over residues should be exactly the splitting rule. Okay, so this is ongoing work with Callum Jones, Paranjape to appear. I've been saying that it's going to appear since December, but hopefully by May it will be done. Okay. Okay, so as I said, this is what we're after, a shift that does this job for you. Now, the shift that does the job for you in this case, so where is our mesh? Yeah. Okay. So yeah. So this is the split that we're looking at now. This is a 4-point amplitude. This is a 4-point amplitude. This is C2 5 star. This is not equal 0, but the rest of them are equal 0. Okay. So the bottommost point over here is x14. The topmost point is x36, which is what sits in your 4-point prefactor. And then your other variables are 1, 3, 2, 4, and then 3, 4, and 4, 6. Okay. So basically, you know the variables that the A bottom depends on, you know the variables that A top depends on, and you know the prefactor. So what we're going to do is precisely take the two x's that correspond to the prefactor and shift them. So you have x14 hat equals x14 plus z. You have x36 hat, which equals x36 minus z. Okay, and now you can write down all the x's in which this possibly has a pole under such a shift. Okay? So that's all of the shifted x's. But how do I know what other x's shift? So as I said, x's form a basis, so you don't actually have to shift anything else. But I want it to be on this kinematics. So I just write down the kinematic conditions, which are C14 equals 0, C15 S15 equals 0, and C24 equals 0. I solve for this, and that tells me that the only shift I need to do is x hat 24 equals x24 plus z. So this is the only other shift I need to do in order to be on this kinematics. Once I do this, I need to figure out what is the residue on this pole. And it turns out, so we saw that when there is a pole, my mesh splits into two triangles in this way, which would be my AL times AR type pole factorization. And it turns out that the zero overlaps either AL, I didn't draw this right, sorry. The zero overlaps AL and AR precisely in a way that it is a zero of the individual subamplitudes. This always happens. So if I go back to my contour integral, dz over z an hat of z, this is a sum over residues. I now know where those residues are. So this is residue at x14 equals 0, plus residue at x36 equals 0, plus residue at x24 equals 0. And basically what we found is that your zero region always overlaps your subamplitudes in a way that this vanishes. So all you get is these two, and these two perfectly reorganize themselves into exactly the splitting rule that you would like. Okay, good. So in a test to see if people are awake, what is the one thing you need to do the residue theorem in BCFW? The one physical ingredient that you need. Yeah. So the contour, the thing that you're integrating, the integrand, needs to vanish at the residue at infinity. There should be no residue at infinity. The integrand needs to fall off. So in other words, good UV behavior is something that you require of your amplitude in order to do residue theorems. So when I write down that residue theorem over there and say that it is giving me splitting near a zero, what I'm really saying is that good UV behavior implies splitting. Okay. I should have pointed out one other thing. But okay, yeah, for now, okay, let me just say that one step of this recursion was assuming lower point zeros, right? So basically, it's good UV behavior plus lower point zeros. And so basically now, and these lower point zeros are given by CK duality. So I can now replace again lower point zeros by CK duality. And so CK duality and good UV behavior now give me splitting near zero. And you'll notice my construction over there, it actually did not shift any of the C variables. So none of my non-planar variables have poles, which means if I do the same exact integral, except now, and I shift the same exact variables, but now for a theory that doesn't have color, a non-planar theory, I still get the same. So I can replace now CK duality with KL derivation. And so this now gives us splitting in all of the theories we've discussed today. So trace phi cubed, NLSM, Young-Mills, Born-Infeld, Young-Mills scalar, gravity, special Galilean, etc. Right? I will say that the spinning theories, it gives it to you in the scaffolded sense. So it gives it to you in the scalar theory. It tells you the scalar theory is splitting, and then you have to go on to the scaffolding residue and see what that means for the spinning theory. But it gives, basically, this slogan level statement is true. So if you asked yourself when you first saw the splitting rule, what is the physical principle behind it? Because if you look at factorization near poles, that's because of locality, unitarity, I mean, basically because of the Feynman propagator in some fashion. So this splitting was very like non-physical. There's no reason to expect this to occur. And in some sense, this whole discussion illustrates what is the physical principle that requires things to have zeros and split. Okay, so that was remark number 1. Yeah, any questions about that? I might have gone a bit, brushed a lot of details aside. Okay, fine. So then let me just talk about remark number 2, which is G vector shifts. Okay, so we heard a little bit about G vectors. If you remember, Alok had this table where when he was drawing his Arkani-Hamed, right? And he could say something like 1, 3 needed to be +1 and -1. Yeah, this construction. I see some nodding heads. Okay. So basically, this was a way for him to construct what is called a G vector, which is basically the normal vector fan to the associahedron. Okay. So if I have, for example, the pentagon that I had before, the normal vector fan would look like this. Okay. So the number of G vectors is the number of boundaries, and you can label your G vectors by precisely which boundary they are normal to, right? So if I redraw this G vector fan for 5 points, I think we don't need this. Yeah. Right. Yeah. So a couple of things about that. The first is there's, I think, as far as I know, no way of seeing a manifestly CK dual form from the Amplituhedron directly. So yeah, that's just one comment that I think so far these have been like 2 completely different approaches to n=4, constructing n=4 integrands. It's like you do the color kinematic thing or you do the momentum twister thing, but there's no mixing them. Which I'm sure you know it, I'm just clarifying. The second thing that you asked was whether you can see the zeros in the Amplituhedron. So generally speaking, for polytopes, there's this thing called the adjoint polynomial. So the adjoint polynomial is saying something like, so even for this guy, right, there are other positions where your boundaries intersect, like this. But it's outside the positive region. And so you need to make sure that there is no pole at this point. And that job is done by the adjoint polynomial. So you would hope that in any polytopic construction, the adjoint polynomial, if you knew it, could give you the position of all the zeros. That being said, yeah, so this is why I started with, you put all of the trace pi cubed amplitudes onto the same denominator and what is the numerator, because that's basically saying what is the adjoint of the associahedron. Okay. And to finally actually answer your question, these are non-supersymmetric. So this, when I say Yang-Mills, I genuinely mean Yang-Mills. I don't mean n=4 super Yang-Mills. Good. So there is a version that I can write down for each of the individual super Yang-Mills amplitudes, but not for the super amplitude. Yeah. So, but then you have to be careful because, so it works for the Yang-Mills, so it works for the vector sector, it works for the scalar sector, that is literally Yang-Mills scalar. And then the question is, does it work for the fermions? All of this is in d dimensions. So how you think about d-dimensional fermions is a very personal question, I think. So like, yeah, so like how you think about d-dimensional supersymmetry is also a question. Good. So I just erased the mesh. But this is, there's inherently you're assuming that all of your x's are independent. Yeah. Yeah, so give me 1 second. So you're assuming that it's independent, and then you go on to this set of s's that are 0. Question is, can you actually go on to that set of s's? Or is it like, theoretically, there is some, I mean, and the point is that once you're in d dimensions, you have d-dimensional constraints, and you may or may not be actually able to reach that configuration. So, for example, in 4 dimensions, if I went on to, I was making this point about how we are one step away from Adler, right? When I was 1, 3 equals 1, 4 equals 1, 5 equals 0 at 6 point. I was saying that if you set one more Mandelstam, you go to Adler. If you look at the gram determinant, so gram of P1, P2, P3, P4, P5, that's the correct number, right? Yeah, okay. This has to be equal to 0 in 4 dimensions. And on the support of this, the gram determinant is actually proportional to C12. So one way of staying in 4 dimensions and achieving the 0 is actually just being Adler. And the other way is whatever else multiplies this. Yeah. So you have to make sure that these are actually achievable in d dimensions. So it's very implicit. Yeah. So none of the actual formulae will look sick. It's just a question of, does this kinematic configuration actually exist in your d-dimensional phase? Other questions? Okay. Yeah. Yeah, okay. So I suppose you could do it for n equals 4, but yeah, fermions, I don't want to talk about fermions. Okay. Okay. Right. So yeah, so we were talking about G vectors over here. So these are the vectors that are normal to the associahedron, the boundaries of the associahedron. And as I said, you can reproduce just this fan of vectors. There are lots of other ways of constructing this G vector fan, but for us, let's think about it in this way. And if I remember correctly, this is G14, G13, G35, G25 and G24. Okay, good. Okay. And so the shifts that we saw earlier are actually very closely related to the following type of shift. Xij hat equals Xij plus vector Gij dotted with some direction t times z. Okay. Gij just contains some +1, -1 signs. And t can be any direction I want in this G space. Okay? And going off in some direction in t, so let's say I went off in this direction to infinity, I'm basically getting rid of this boundary. But I still have some shape. And so the question that we wanted to answer, this is also upcoming work with a student at Brown, Marcos Kofronik, Marcus Pradlin, Anastasia Volovich. Hopefully, again, to appear next month. But yeah, so basically you do these shifts, and when you send z to infinity, you get amplitudes in quotes. So these are amplitudes in the sense that the accordiahedra that Alok introduced are amplitudes. They factorize correctly, they have well-defined poles, and they'll always give you a rational function. So yeah, so these are amplitudes, but in some cases, okay, so in special cases, you can remove the quotes. So these are actually amplitudes of known friendly theories that people study. So in particular, you can get, for example, if you do Yeah, let's do an example. Okay, so example, n equals 5. So the G vector fan we have over there, we choose the direction 1, 1. Okay. Now, 1, 1 means that I have shifted, where is it? Yeah, here. It means that I'm shifting along these two directions, G14 and G13. So that means that x13 hat is x13 plus z, x14 hat is x14 plus z, x, what are the others? 2, 5 and 3, 5. 2, 5 minus z. And you can see that because these are just opposite to these directions. So they shift in the opposite direction. And then finally, x 2, 4 hat is unshifted. Okay. So when I take z to infinity, all of the poles in these variables vanish. They go away, right? So the only pole that I'm left with is at x24, which means that this is the graph. There's a singular graph and it is 2, 4. So 2, 3, 4, 5, 1. Okay. In addition, I can look at what is happening to the c's. So yeah, so various c's remain constant. 1, 4, 2, 4, 2, 3. Sorry, not 2, 3. These, yeah, these. So these remain constant. What this means is that I still have a 0 when C13 equals C14 equals 0, and when C14 equals C24 equals 0. And turns out you can use this fact to say that my particle 1 and particle 4 are pions. And so this amplitude is actually just 1 pion, 2, 5, 3, 5, 4 pion, 5, 5. This is an amplitude. It's a mixed amplitude. There's of course the interesting case of, so let's say n equals 6, t equals 101, and then you actually just get an LSM of all pions. Okay. Yeah. Okay. So again, you can play the same game in this case. You can look at which C's are preserved. So which ones, which ones still have a 0. In this case, all of them will have a 0, but very few poles will be preserved. And that will tell you exactly what kinds of diagrams you're allowed to have. And in addition, the actual interaction will be dictated by what 0 is, because that is telling you what is the numerator of that graph. Yeah. Okay. Right. So the last comment that I had is again to appear in this paper soon, hopefully, is that in the particular case of an pi, let's say pi 5, something special happens. So if you look at the singular graph that can contribute to this, there is only, actually, okay, let's do this. There is only this one. So these are all 5s. This is pi, this is pi, this is pi. There's only one graph that can occur. So if you look at your n-dimensional polytope, what this means is that there is always one chord which is x14. Okay, 1, 2, 3, 4. Always x14. But ignoring what is to the right of this, This part is just a phi cubed amplitude. This is just an associahedron. So what this means is there is a polytopic description for all amplitudes that have 2 pions and the rest phis. Right? This polytopic description will literally be whatever this subamplitude is. There is a way of saying exactly what that is, and then the lower point associahedron. It's a very simple construction of a new set of amplitudes in a new theory that actually directly has a polytopic interpretation without doing your, you write down the canonical form, you shift it, you get another amplitude. This is directly in kinematic space writing down a polytope for this set of amplitudes, any 2 pion amplitude. Yeah. So that will be, as I said, PSSV, hopefully to come out very soon. Okay, I think that's basically all I wanted to say. If you're interested in talking about wave function coefficients, I'm happy to do it not recorded. But for now, I think let me just end here a few minutes early. Yeah, thanks.
Other questions? What are your comments on wave function correlators?
Okay, so I don't know how much I should say because it's work in progress, but basically, if you look at the graphs that you're drawing, right? For example, at 5 point, you draw something like this, and then you associate to this graph. So 1, 2, 3, 4, 5. You associate to this graph 1, 3, and 1, 4. Now, the fact that you're thinking about these x's as living, so usually you think of these x's as living on some circle. That's why xij is the same as xji, and you have these things. But you could instead artificially think of them as living on a line, where I've just removed some boundary condition. Yeah. And then I can do the following interpretation, which is that x13 is this, x14 is this. And then all of these graphs are in 1-to-1 correspondence with flat space wave function coefficients. So all of the machinery that comes from having an associahedron, in particular an ABHY associahedron, will be inherited by these graphs. Now, of course, these are only if the graph that you're looking at for the wave function coefficient is a chain. So we then extend this to things that are not chains as well. Yeah. And in particular, then you can, as I said, all of the machinery that I just discussed will be inherited by these objects. Yeah. So that I should say is work with Sean Akte, me, Andrei Pokraka, Marcus Pradlin, and Anastasia Volovich. Also to appear. I'm just writing things up. I'm not being very good about it, but yeah. So basically all of the machinery is inherited by these guys, who will ultimately be then integrands of FRW wave functions. I will say there is an open question, which is how much knowing the zeros of an integrand helps you. Yeah, which is, I think, something that I want to think more about, which is, can that actually help you in any way, knowing that your integrand vanishes, not your integral. I think everyone wants coffee.
Are there other questions? Okay, so then thank you, Shruti, for a very nice set of lectures, and we'll break for coffee, and we'll be back at 11.